Hello out there, welcome to this tutorial on circle theorems. So we are going to solve some of those theorems on circle geometry. So before then, let's take a look at lines of a circle. I will consider this circle. Here O is the center of the circle. Then from the center of the circle to any part of the circumference, we call it R, and R is the radius of the circle. And from one part of the circumference to the other part of the circumference, passing through the center of the circle, we call it D, and D is the diameter of the circle. Again, from one part of the circumference to the other part of the circumference, for which the line is not passing through the center of the circle, we call it X, and X is the chord of the circle. Then again, the distance round the circle, we call it a C, where C is the circumference of the circle. And from here we have this is a radius, this is another radius. Then the line between two radii, so we call it A, and A is the arc of the circle. So these are the lines of a circle with their various names. Now we look at the regions of a circle. Now consider this circle center O. I have a chord, and this chord is dividing the circle into two regions. The bigger one is the major segment, and the part not shaded is the minor segment. So a chord of a circle divides the circle into two segments. The bigger one is the major segment, while the smaller one is the minor segment. And we go further, we have another circle center O. We have radius, another radius. These two radii divide the circle into two sectors. So we shade the larger sector, which is referred to as major sector, and the sector that is not shaded is called the minor sector. So two radii divide a circle into two sectors, the bigger being the major sector and the smaller being the minor sector. So from here we can now consider some of the circle theorems. So the circle theorem here is about the midpoint of a chord of a circle. So the theorem is stated here: a straight line drawn from the center of a circle to bisect a chord which is not diameter is perpendicular to the chord. So we look at the circle center O, and they said a straight line drawn from the center of a circle to bisect a chord. So we need chord X, Y, and the straight line drawn from the center is not a diameter, and is perpendicular to the chord. That is, the angle between this line from the center to the chord is 90 degrees. And it divides the line XY into two, where this is the midpoint, that is, this side is equal to this side. So we will state it that in the diagram XY is a chord, OM is the perpendicular to XY, and XM is equal to MY. That is what the theorem is all about. So we go ahead to solve some problems based on the theorem of midpoint of a chord. So we take our first problem. Problem 1. The midpoint of a chord 16 centimeters long is 6 centimeters from the center of the circle. Calculate the radius of the circle. We have to give the diagram of the whole thing to enable us visualize the problem and solve appropriately. Now we draw a circle, center O. We have a chord, so we name the chord XY, and a line is drawn from the center to the midpoint of the chord. So we have the line, and this line is at right angle to XY. Since this is going to be the midpoint, call it M. Since the chord is 6 centimeters from the center of the circle, we have 6 centimeters, and the XY is 16. Therefore, XM here will be 8 and MY will be 8. That is the theorem of midpoint of a chord. Now we are looking for the radius, so we join OX. So joining OX, we call it R. Since this triangle XOM is a right angle, we go by Pythagoras theorem. That is, this is the hypotenuse, R is the hypotenuse, so we have R squared equal to 6 squared plus 8 squared. That will give us 36 plus 64, which gives 100. R squared is 100, which means R is square root of 100, and square root of 100 is 10 centimeters. Therefore, the radius is 10 centimeters. So we have done justice to problem 1. We go to problem 2. So problem 2. What is the distance of the midpoint of a chord 24 centimeters from the center of the circle, radius 13 centimeters? Again, we are going to give the diagram here. This is a circle, center O, and we know we always have a chord, and we call it XY. It is not always XY, and the chord is certain distance from the center of the circle, which is right angle, and this is the midpoint. What is the distance of the midpoint of a chord 24 centimeters from the chord is 24 centimeters, though this will be 12, this will be 12, and radius 13 centimeters. That is OX is 13 centimeters. We are to calculate the midpoint of the chord from the center of the circle. We can call this one X. And again, by Pythagoras theorem, this is the hypotenuse. So since we have hypotenuse, we are looking for the other side. So we are going to have it as x squared equal to 13 squared minus 12 squared. So 13 squared is 169 minus 144, and this will give us 25. Since x squared is 25, so x is square root of 25, which gives 5 centimeters. Therefore, the midpoint of the chord is 5 centimeters from the center of the circle. So we go ahead to problem 3. For problem 3, the midpoint of a chord is 6 centimeters from the center of the circle of radius 15 centimeters. Calculate the length of the chord. We have to calculate the length of the chord here. So still from our diagram, this is this. Still starting with our diagram, a circle with center O and the chord is XY. we have to have a line from the center of the circle to the chord, which is perpendicular, and that is M, the midpoint of X and the Y, and the chord is 9 centimeters from the center of the circle. So this is 9, and radius is 15. So XM is equal to MY. We call it X here, and MY is X. So we find the value of X, and to get XY, we add or multiply the value of X by 2 to get the length of the chord. So by Pythagoras theorem, we have this is the hypotenuse, so we are looking for the other side. So we have x squared equal to 15 squared minus 9 squared. 15 squared is 225 minus 81. 225 minus 81 from your calculator, we have it as 144. So x is square root of 144, which gives 12. Therefore, the length of the chord is 2 times 12, which gives 24 centimeters. And we have done justice to problem 3. We go to problem 4. For problem 4, a circle has radius 7 centimeters. 2 parallel chords lie opposite sides of the center of the circle. The lengths of the chords are 10 centimeters and 12 centimeters respectively. Calculate correct to the nearest 0.1 centimeters. That's 1 decimal place. The distance between the chords. Oh God, we still need a circle. Center O, 2 chords, opposite sides. So we have the first chord here and the other chord here, since they are parallel. So we draw the line from the center to touch the 2 chords. And the radius now, the radius here is 7 centimeters, and also the other radius here is 7 centimeters. So we can name the lines. This is A, B, where this midpoint here is M. Here we have it as P, Q, and the midpoint here is N. We are told that the length of the chords are 10 centimeters and 12. Since M is the midpoint, so we can get AM by dividing 10 by 2, which gives 5. And also here, PN, that's going to give us 12 divided by 2, which gives 6. But to calculate the distance between the 2 chords, that's to say we are calculating MN. We calculate line MN, call this one X and call this one Y. We find X and Y, add them together to give us the distance between the 2 chords. So we start with triangle AMO, and to get X using Pythagoras theorem, we have X squared is equal to 7 squared minus 5 squared. That's Pythagoras theorem. This will give us 24, and X is square root of 24 from our calculator. This is not a perfect square. That will give us 4.899 centimeters. So we've gotten the value of X. We also go ahead to calculate the value of Y. From triangle PON, we are looking for Y, which is not the hypotenuse. So Y squared will be equal to the square of the hypotenuse minus the square of the other sides. This is Pythagoras theorem. This will give us 13. Now square root of 13 to get Y. is going to give us 3.606 centimeters. So x plus y now will be 8.505 centimeters, and they said to the nearest 0.1 centimeters, that's to the nearest 1 decimal place. So that will give us 8.5 centimeters, and this is to 1 decimal place, which is the same thing as to the nearest 0.1 centimeters. So we have the distance between the chord to be 8.5 centimeters. Now we go to the next problem. Problem 5. An equilateral triangle of sides 12 centimeters is inscribed in a circle. Calculate correct to 2 significant figures. A. The radius of the circle. B. The midpoint of one side from the center of the circle. So we are going to draw the circle center O, the equilateral triangle. Then we have the radius from the center of the circle to one of the vertices of the triangle. Now the distance from the center of the circle to one of the sides. And remember, the equilateral triangle, all the sides are equal, all the angles are equal. So this radius is a bisector of the angle here. So this angle will be 30 degrees. This is radius. Now this line from the center to one of the sides here is perpendicular bisector. If we name this point A, B, this is the midpoint. Since AB is 12 centimeters, so we are going to divide it into 2 to get AM, which is also equal to MB. So we have AM here to be 6 centimeters, and the distance from the center to M, that is OM, will be named X. So we are meant to calculate the radius, which is problem A, and the midpoint of one side from the center of the circle, which we have labeled as X. Now we're going to use trigonometric ratios to solve this problem. Since this is a right angle triangle, we know one of the angles, and we are given this is the adjacent, the opposite, and the hypotenuse. So starting from problem A, that's the radius, we calculate R first. So this is adjacent and hypotenuse. So the ratio connecting adjacent and hypotenuse is cosine. So we have the cosine 30 degrees is equal to adjacent, which is 6 over hypotenuse, and that will be over R. So if we make R the subject of the relation, we have R equal to 6 over the cosine of 30 degrees is 0.866, and if you press your calculator, we have R to be 6.928 centimeters. To 2 significant figures, we are going to have it as 6.9. This is the first significant figure, the second significant figure. The third number is not up to 5, so we round it down. So we have our final answer as 6.9 centimeters to 2 significant figures. So that's the solution of problem 5A. We go to problem B. For problem B, we are going to look for the value of X. So that's going to be opposite and adjacent, and the ratio connecting opposite and adjacent is tangent. So we have tan 30 degrees is equal to opposite, that's X, over adjacent, which is 6. So making X the subject of the relation, X will be equal to 6 multiplied by tan 30 degrees is 0.5774. So multiplying this out, we have X equal to 3.464 centimeters, and to 2 significant figures, This is the first significant figure. The third one is 6. Since it is more than half of 10, we make it 1. That's, we round it up and make this 5. So our final answer will be 3.5 centimeters to 2 significant figures. So we go to problem 6. For problem 6, in the diagram below, O is the center of the circle. This is O, P, Q, R. OM is a perpendicular to PR. PM is 12 centimeters. QM is 8 centimeters. And PO is X centimeters. Find the value of X. Now, this is a right angle triangle. PO is X and OQ is also X. They are both radii since they are from the center of the circle. Since OQ is X and QM is 8, which means OM here is X minus 8. X minus 8 will give us OM. Now from triangle POM, we can use Pythagoras theorem. This is the hypotenuse. We have x squared is equal to 12 squared plus x minus 8 squared. We expand. So this is 144 plus x squared minus 16x plus 64. If you expand this bracket, you have x squared minus 16x plus 64. Now collecting the terms with x on the left hand side, we have x squared minus x squared plus 16x is equal to 64 plus 144. So x squared minus x squared is gone. So we have 16x equal to 208. 208 divided by 16. So x is equal to 13. So we have done justice to problem 6. This is the end of this video. Our next circle theorem or theorems on our next video. Check the description section of this video on our YouTube channel for subsequent videos on circled theorems. Until we come your way again, goodbye.